On a cool November evening in 1967, at the Mullard Radio Astronomy Observatory near Cambridge, England, graduate student Jocelyn Bell Burnell noticed something unusual in the data streaming from a newly constructed radio telescope. The telescope, spanning 4.5 acres of the English countryside, had been designed to study quasars, those mysterious, intensely bright objects discovered just a few years earlier in the distant universe. But what Bell Burnell discovered that evening would prove to be something entirely different, something no one had predicted. The radio telescope array consisted of 2,048 dipole antennas arranged in neat rows across a field, connected by miles of wire and cable. It operated at a frequency of 81.5 megahertz, in the same part of the radio spectrum used by FM radio stations on Earth. The instrument was designed to detect the twinkling of radio sources caused by the solar wind, the stream of charged particles flowing outward from the sun. This scintillation effect, similar to how stars twinkle in visible light due to Earth's atmosphere, could help astronomers identify quasars among the thousands of radio sources in the sky. Bell Burnell's job involved analyzing the chart recorder output from the telescope, which produced nearly 100 feet of paper charts every day. These charts showed squiggly lines representing the intensity of radio emissions detected by the telescope as it swept across the sky. Most of the time, the lines showed relatively smooth variations or occasional bursts of noise from terrestrial interference. But on this particular evening, Bell Burnell noticed a small section of chart where the signal showed a regular, repeating pattern unlike anything she had seen before. The signal consisted of rapid pulses, each separated by a remarkably precise interval of approximately 1.3 seconds. The pulses themselves were incredibly brief, lasting only about 30 milliseconds, or 0.03 of a second. What made this particularly intriguing was the regularity of the timing. Natural astronomical sources typically produce either steady emissions or random variations, not precisely timed pulses like a cosmic metronome. Bell Burnell showed the chart to her thesis advisor, Annie Hewish, who had designed and built the radio telescope. Initially, they wondered if the signal might be terrestrial interference, perhaps from some electrical equipment or a radio transmitter. But several factors argued against this explanation. The signal appeared at the same celestial position each night, rising and setting with the stars rather than remaining fixed relative to Earth. This meant the source was astronomical, not terrestrial. The team began monitoring the signal more closely, using higher time resolution equipment to study its characteristics. They confirmed that the pulses arrived with extraordinary regularity, their period stable to within milliseconds day after day. The precision of this timing was unlike anything known in nature at that time. The regularity was so remarkable that the team briefly and somewhat humorously considered the possibility that the signal might be artificial, a beacon from an extraterrestrial civilization. They privately referred to the source as LGM-1, standing for Little Green Man. However, the extraterrestrial hypothesis quickly became untenable when Bell Burnell discovered more of these pulsing radio sources in other parts of the sky. By early 1968, she had identified 3 more sources, each with different pulse periods ranging from about 1/4 of a second to just over a second. The existence of multiple sources with different characteristics suggested a natural phenomenon rather than artificial signals. The discovery was announced to the scientific community in February 1968 in a paper published in the journal Nature. The paper, authored by Hewish, Bell Burnell, and their colleagues, described these new objects and suggested they might be oscillating white dwarf stars or neutron stars, though the exact nature remained uncertain. The astronomical community immediately recognized the significance of the discovery, and observatories around the world began searching for more of these pulsing radio sources. Within months, dozens more pulsars had been discovered, each with its own characteristic pulse period. The periods ranged from fractions of a second to several seconds, and all showed the same remarkable timing stability. Astronomers quickly realized they had discovered a new class of astronomical object, one that would prove invaluable for understanding the universe and would eventually become known as nature's most accurate natural clocks. The name pulsar was coined by a science journalist as a contraction of pulsating star. Though as scientists would soon learn, these objects were not truly pulsating in the sense of expanding and contracting. Instead, they were rapidly rotating neutron stars, the collapsed cores of massive stars that had exploded as supernovae. Each pulse represented a beam of radio waves sweeping past Earth like the beam from a lighthouse as the neutron star spun on its axis. This discovery marked the beginning of a new era in astronomy. Pulsars would provide insights into the behavior of matter under extreme conditions, allow tests of Einstein's theory of general relativity, help map the structure of our galaxy, and even lead to the discovery of planets orbiting other stars. The precise, unwavering rhythm of their pulses would transform them from a curiosity into one of astronomy's most valuable tools. As the world awakened to the existence of pulsars, scientists began to appreciate that these rapidly spinning stellar remnants offered something unprecedented: natural clocks of extraordinary precision scattered throughout the cosmos. The story of pulsars had just begun, a story of cosmic timekeeping that would reveal fundamental truths about the universe and demonstrate nature's ability to create mechanisms of breathtaking precision and regularity. In the quiet countryside of Cambridge, where this remarkable discovery had been made, the radio telescope continued its nightly vigil, sweeping across the heavens and recording the rhythmic pulses from distant neutron stars. Each pulse represented the spin of a stellar corpse, a collapsed star no larger than a city, yet containing more mass than the sun, rotating with a regularity that would make the finest atomic clocks seem imprecise by comparison. To understand pulsars and their extraordinary properties, we must first journey into the violent death throes of massive stars. For pulsars are born in the most powerful explosions in the universe, supernovae. The story of a pulsar begins billions of years earlier, with the birth of a massive star, and follows that star through its entire lifetime to its spectacular demise. Stars form from vast clouds of gas and dust called molecular clouds, which drift through the galaxy, sometimes spanning hundreds of light years. When regions within these clouds become dense enough, gravity begins to pull the material together. As the cloud collapses, it fragments into smaller clumps, each of which may eventually become a star. The material in these collapsing clumps falls inward, heating up through compression until the core becomes hot and dense enough for nuclear fusion to begin. 4 stars with masses more than about 8 times the sun's mass. The fusion process will eventually progress through several stages. First, hydrogen fuses into helium in the core, producing the energy that makes stars shine. This stage lasts for millions of years, with more massive stars burning their fuel more rapidly than smaller ones. When the hydrogen in the core is exhausted, the core contracts and heats up until it becomes hot enough to fuse helium into carbon and oxygen. This process continues with ever heavier elements. Carbon fuses into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, and finally silicon into iron. Each successive fusion stage produces less energy and proceeds more quickly than the last. A massive star might spend millions of years fusing hydrogen, thousands of years fusing helium, but only a few years fusing carbon, and just days fusing silicon into iron. Throughout this process, the star develops an onion-like structure with layers of different elements, each at different temperatures and densities, surrounding the ever-contracting core. The fusion of silicon into iron marks a critical turning point. Iron is the most stable element in terms of nuclear binding energy, meaning that fusing iron into heavier elements requires energy input rather than releasing energy. When the core becomes primarily iron, it can no longer generate energy through fusion. Deprived of the outward pressure from fusion that has been supporting it against gravity throughout its life, the core becomes unstable. What happens next occurs with stunning speed. The iron core, typically about 1.5 times the mass of the Sun, compressed into a sphere roughly the size of Earth, suddenly collapses. In less than a second, the core implodes, its material falling inward at speeds approaching 1/4 the speed of light. As the collapse proceeds, the density skyrockets beyond anything found in normal matter. Electrons are forced to combine with protons through a process called electron capture, producing neutrons and neutrinos. The neutrinos, which interact only weakly with matter, stream outward, carrying away enormous amounts of energy. Meanwhile, the collapse continues until the core reaches densities comparable to atomic nuclei, about 100 trillion times the density of water. At this point, nuclear forces become important, creating a pressure that resists further compression. The infalling material rebounds off this incredibly dense core, launching a shock wave outward through the star. This shock wave, energized by the intense neutrino flux from the core, blasts through the star's outer layers, heating and accelerating them to tremendous speeds. The outer layers are ejected into space in a titanic explosion called a core collapse supernova, one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. The light we see from a supernova comes primarily from the decay of radioactive elements created in the explosion, particularly nickel, 56, which decays through cobalt, 56 to iron, 56. Left behind at the center of the expanding debris is the collapsed core, now transformed into a neutron star. This remnant contains about 1.4 to 2 times the Sun's mass, compressed into a sphere only about 12 miles in diameter, roughly the size of a city. To comprehend this density, imagine crushing all the mass of the Sun into a ball small enough to fit within the island of Manhattan. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars represent one of the most extreme states of matter in the universe. Their surface gravity is approximately 200 billion times stronger than Earth's, strong enough that the escape velocity from a neutron star surface is about 1/3 the speed of light. The intense gravity compresses matter to such densities that the atoms are completely crushed, with electrons and protons forced together to form neutrons. The resulting material, primarily neutrons with small amounts of protons and electrons, exhibits properties unlike anything found on Earth. The interior structure of a neutron star likely consists of several layers. The outer layer, called the crust, is about 1 mile thick and consists of iron nuclei embedded in a sea of electrons. Deeper in the crust, at higher densities, the nuclei become increasingly neutron-rich until free neutrons appear. Below the crust lies the outer core, where matter exists as a superfluid of neutrons with some protons and electrons. The inner core, at the very center of the neutron star, remains poorly understood, but may contain exotic forms of matter, such as hyperons or even quark matter, where neutrons break down into their constituent quarks. Neutron stars also possess extraordinarily strong magnetic fields, typically about 1 trillion times stronger than Earth's magnetic field. These intense magnetic fields are believed to be produced by the compression of the progenitor star's magnetic field during core collapse. As the core shrinks, conservation of magnetic flux concentrates the magnetic field lines, amplifying the field strength to tremendous values. In some neutron stars called magnetars, the magnetic fields can reach even more extreme values, up to 1,000 trillion times Earth's field. Another consequence of stellar collapse is rapid rotation. Most stars rotate at least slowly, and as they collapse, conservation of angular momentum causes their rotation rate to increase dramatically, just as a figure skater spins faster when pulling in their arms. A star that initially rotated once every few weeks might, after collapsing to a neutron star, rotate several times per second or even hundreds of times per second. This combination of properties, rapid rotation and strong magnetic fields, sets the stage for the pulsar phenomenon. The rotating magnetic field generates electric fields near the neutron star's surface, accelerating charged particles to nearly the speed of light. These particles emit beams of radiation along the magnetic poles of the neutron star. If the magnetic axis is tilted relative to the rotation axis, as it usually is, these beams sweep through space like lighthouse beams as the neutron star rotates. When one of these beams happens to point toward Earth, we detect a pulse of radiation, and we observe the neutron star as a pulsar. The birth of a neutron star in a supernova explosion is thus also the birth of a potential pulsar, a cosmic lighthouse that will spin with extraordinary regularity for millions or even billions of years. These spinning stellar remnants, forged in the most violent events in the cosmos, become the universe's natural timekeepers, their pulses marking time with a precision that rivals the best human-made clocks. Understanding pulsars requires understanding how these rapidly spinning neutron stars produce their characteristic beams of radiation. The pulsar mechanism, though complex in its details, can be understood through the lighthouse analogy, where beams of radiation sweep through space as the neutron star rotates. The lighthouse comparison is apt, but the actual physics involves some of the most extreme conditions and powerful electromagnetic forces in the universe. At the heart of every pulsar lies a neutron star rotating at tremendous speed. The rotation periods observed in pulsars range from about 1.4 milliseconds for the fastest known pulsars to more than 8 seconds for the slowest. Most pulsars have periods between about 0.25 seconds and 2 seconds. These rotation rates mean that the neutron star surface at the equator moves at speeds ranging from about 20,000 miles per hour for the slowest pulsars to over 40,000 miles per second for the fastest, approaching 25% of the speed of light. The neutron star's magnetic field plays a crucial role in the pulsar mechanism. This field, anchored in the neutron star's interior, rotates with the star. The field structure is approximately dipolar, like a bar magnet, with magnetic field lines emerging from one magnetic pole, arcing through space, and returning at the other pole. The magnetic axis, the line connecting the magnetic poles, is typically tilted at some angle relative to the rotation axis. As the magnetized neutron star rotates, the magnetic field lines are forced to rotate with it. Close to the neutron star, within a region called the magnetosphere, the magnetic field is strong enough to force charged particles to co-rotate with the star. This co-rotation cannot extend indefinitely into space because at some distance from the neutron star, the co-rotation speed would equal the speed of light, which is physically impossible. This critical distance defines a boundary called the light cylinder. The light cylinder radius depends on the pulsar's rotation period. For a pulsar with a 1-second period, the light cylinder lies about 30,000 miles from the neutron star. For faster pulsars with millisecond periods, it is proportionally closer. Beyond the light cylinder, magnetic field lines cannot remain closed and are dragged out into interstellar space, forming an extended magnetotail somewhat like Earth's magnetotail, but far more energetic. The region where the physics becomes most interesting is near the magnetic poles of a neutron star. The intense magnetic field at the surface, combined with the neutron star's rapid rotation, creates enormous electric fields parallel to the magnetic field lines. These electric fields can reach values trillions of times stronger than the strongest electric fields achievable in laboratories on Earth. These electric fields are capable of pulling charged particles from the neutron star surface despite its immense surface gravity. Once liberated, electrons and positrons, the antimatter counterparts of electrons, are accelerated to extremely high energies along the curved magnetic field lines. As these particles are accelerated, they emit electromagnetic radiation through several processes. The primary mechanism is curvature radiation, emitted when charged particles moving at nearly the speed of light follow the curved paths defined by the magnetic field lines. The high-energy photons produced by the accelerating particles can interact with the magnetic field and with each other. While high-energy gamma-ray photon passes through the intense magnetic field near the pulsar, it can convert into an electron-positron pair. These newly created particles are then accelerated by the electric field and emit more photons, which can create more pairs, leading to a cascading process that generates an enormous flux of particles and radiation. This cascade develops primarily above the magnetic poles, creating two cone-shaped emission regions that extend outward along the magnetic field lines. The radiation emitted in these regions forms narrow beams that sweep through space as the neutron star rotates. The exact opening angle of these beams depends on the pulsar's properties, but typically they extend over a cone with an opening angle of a few to perhaps 20 degrees. Most pulsars emit radiation across a broad range of the electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. However, pulsars are most commonly detected at radio wavelengths, and the radio emission mechanism remains somewhat mysterious despite decades of study. The radio emission is remarkably bright considering it comes from such a small region, and it shows a phenomenon called coherence, meaning that many particles radiate in phase, amplifying the total emission. The radio emission appears to originate from regions somewhat above the neutron star's surface, perhaps at altitudes of tens to hundreds of miles. The exact location and mechanism of radio emission generation are subjects of ongoing research, but likely involve plasma instabilities or resonant wave-particle interactions in the pulsar magnetosphere. The emitted radio waves then propagate outward through the magnetosphere, sometimes showing evidence of scattering and absorption by the magnetospheric plasma. When we observe a pulsar from Earth, we see one or sometimes two pulses per rotation, depending on whether one or both magnetic pole beams sweep past our line of sight. The pulse shape, called the pulse profile, is remarkably stable for a given pulsar, showing the same pattern of peaks and troughs rotation after rotation. Some pulsars show a single main pulse, others show a main pulse and one or more smaller interpulses, and still others show complex multi-component profiles. The pulse profile contains information about the geometry of the emission region and the structure of the magnetic field. By studying how the polarization of the radio waves changes across the pulse profile, astronomers can determine the angle between the magnetic and rotation axes and the angle at which our line of sight cuts through the emission beam. This geometric information helps us understand the three-dimensional structure of the pulsar's magnetosphere. Some pulsars show dramatic intensity variations between individual pulses, a phenomenon called pulse nulling. During nulling episodes, which can last from a few rotation periods to thousands of rotations, the pulsar's radio emission becomes undetectable or greatly reduced. Then, without warning, normal pulsing resumes. The cause of nulling remains uncertain, but may involve changes in the magnetosferoplasma conditions that temporarily disrupt the emission mechanism. Other pulsars show sudden changes in their pulse profiles and rotation rates called glitches. These glitches are believed to result from sudden rearrangements in the neutron star's interior structure, possibly involving the superfluid components of the neutron star. When a glitch occurs, the pulsar's rotation rate increases abruptly by a tiny fraction, typically a few parts per million, then gradually returns toward its pre-glitch behavior over weeks to months. The pulsar lighthouse mechanism, with its combination of rapid rotation, intense magnetic fields, and relativistic particle acceleration, creates one of nature's most precise and stable signals. The regularity of pulsar pulses, arriving like clockwork rotation after rotation, makes these objects invaluable as cosmic timekeepers. Each pulse marks another rotation of a neutron star, a stellar remnant no larger than a city spinning at rates that would tear apart any normal material, generating beams of radiation that sweep through the cosmos like the beam from an impossibly bright and perfectly regular lighthouse. One of the most important characteristics of pulsars is that they do not maintain constant rotation rates forever. Over time, all pulsars gradually slow down, their rotation periods lengthening by tiny amounts year after year. This spin-down, as it is called, provides crucial information about pulsars' energy output and evolution, and the precise measurement of spin-down rates has become central to using pulsars as tools for fundamental physics. When Jocelyn Bell Burnell first discovered pulsars in 1967, their pulse periods seemed remarkably stable. However, within a few years of careful timing observations, astronomers detected that pulsar periods were gradually increasing. The Crab pulsar, one of the first pulsars discovered and one of the youngest known, was found to be slowing down at a rate of about 38 nanoseconds per day. This might seem insignificant, but over a year this amounts to about 14 microseconds, easily measurable with precise timing observations. The cause of this spin-down is the loss of rotational energy. As the pulsar's magnetic field rotates with a neutron star, it generates electromagnetic radiation and accelerates particles in the magnetosphere. This requires energy, which is supplied by the neutron star's rotational kinetic energy. As the pulsar pours energy into radiation and particle acceleration, it must slow down to conserve angular momentum and energy. The rate at which a pulsar slows depends on several factors. Most importantly, its magnetic field strength and rotation rate. Pulsars with stronger magnetic fields and faster rotation rates emit more energy and therefore slow down more rapidly. The relationship between rotation period, magnetic field strength, and spin-down rate allows astronomers to estimate a pulsar's magnetic field strength from timing observations alone, without needing to measure the field directly. For a typical young pulsar with a period around 1 second and a magnetic field of about 1 trillion times Earth's field, the spin-down rate might be several microseconds per year. The Crab pulsar, which has a period of 33 milliseconds and is losing energy very rapidly, slows down about 36 microseconds per year. In contrast, millisecond pulsars, which are old, recycled pulsars with much weaker magnetic fields, slow down at extraordinarily small rates, sometimes just a few nanoseconds per year or even less. The energy lost by a slowing pulsar is tremendous. The Crab pulsar, for example, is losing rotational energy at a rate of about 100,000 times the total power output of the Sun. This enormous energy output powers the Crab Nebula, the expanding remnant of the supernova that created the pulsar in the year 1054 AD. The pulsar's energy drives the nebula's glow, accelerates particles to ultra-high energies, and maintains the complex filamentary structure seen in telescopic images. By measuring a pulsar's current period and its rate of change, astronomers can estimate the pulsar's characteristic age, essentially how long it has been slowing down at its current rate. This calculation assumes that the pulsar was born spinning rapidly and has been slowing down at a constant rate determined by its current properties. While this gives only an approximate age, since the actual spin-down rate changes as the pulsar slows, it provides useful estimates for comparison between pulsars. The characteristic ages of pulsars span an enormous range. The youngest known pulsars have characteristic ages of just a few thousand years and are associated with recent supernova remnants visible at optical, X-ray, and radio wavelengths. These young pulsars spin rapidly, have strong magnetic fields, and slow down quickly. The Crab pulsar has a characteristic age of about 1,240 years. reasonably close to its true age of about 970 years since the supernova was observed. At the other extreme, millisecond pulsars have characteristic ages of billions of years, often comparable to or exceeding the age of the universe. These ages are not meant to be taken literally, but indicate that these pulsars are old objects that have been spun up or recycled through mass transfer from a companion star, a process we will explore later. The extremely slow spin-down rates of millisecond pulsars make them exceptionally stable timekeepers. Timing observations of pulsars have revealed that spin-down is not perfectly smooth. Occasionally, pulsars experience sudden spin-ups called glitches, where the rotation period abruptly decreases by a tiny amount, typically a few parts in a million. After a glitch, the pulsar gradually returns toward its pre-glitch behavior, though it may not fully recover. Glitches are believed to result from interactions between the neutron star's crust and its superfluid interior. The interior of a neutron star likely contains neutrons in a superfluid state, meaning they flow without viscosity. As the neutron star slows down, its crust spins slower while the superfluid interior, which is only weakly coupled to the crust, maintains its rotation rate. This differential rotation builds up stress until suddenly the superfluid couples to the crust, transferring angular momentum and causing a glitch. The Vela pulsar, one of the brightest pulsars in the radio sky, glitches every 2 to 3 years, providing opportunities to study this phenomenon. The long-term spin-down of pulsars means they have finite lifetimes as detectable radio sources. As a pulsar slows down and its magnetic field decays over millions of years, it eventually reaches a point called the death line, where it can no longer generate the electric fields necessary to produce radio emission. At this point, the pulsar effectively turns off as a radio source, though the neutron star continues to exist and rotate, just no longer emitting detectable pulses. The population of pulsars in our galaxy reflects this evolution. Young pulsars are bright and easily detected, but relatively rare because supernovae producing neutron stars occur only a few times per century in our galaxy. Middle-aged pulsars are more common, having had time to accumulate while still being detectable. Old pulsars that have not been recycled are largely invisible to our telescopes, having crossed the death line. Millisecond pulsars, despite being old, remain detectable because they have been spun up to rapid rotation rates through accretion from companion stars, rejuvenating them as radio emitters. The precise measurement of pulsar spin-down rates requires careful timing over months to years. Astronomers observe pulsars regularly, measuring the arrival times of pulses at their telescopes. These times of arrival must be corrected for the motion of Earth around the Sun and for various propagation effects as the radio waves travel through interstellar space. By fitting a model to the arrival times, they could determine the pulsar's period and its rate of change to extraordinary precision. For the most stable pulsars, particularly millisecond pulsars, timing precision can reach tens of nanoseconds or better, allowing detection of period changes as small as a few parts in 10 trillion per year. This extraordinary precision has enabled the use of pulsars to test fundamental physics, search for gravitational waves, and even discover planets orbiting neutron stars. The gradual, predictable slowing of pulsars, combined with the precision with which it can be measured, transforms these spinning neutron stars into cosmic clocks of remarkable accuracy and stability. Among all pulsars, a special class stands out for their extraordinary properties: millisecond pulsars, which rotate hundreds of times per second, far faster than typical pulsars. These rapidly spinning neutron stars are the most precise natural timekeepers in the universe, with stabilities rivaling the best atomic clocks humans have constructed. Their existence posed a mystery when first discovered, as their rapid rotation and weak magnetic fields seemed inconsistent with standard pulsar evolution. The solution to this puzzle revealed a fascinating process of stellar evolution and rejuvenation. The first millisecond pulsar was discovered in 1982 by astronomers Don Backer, Sri Kulkarni, Carl Hiles, Michael Davis, and Miller Goss, using the Arecibo radio telescope in Puerto Rico. They detected a pulsar in a globular cluster designated PSR B1937 plus 21, later refined to PSRJ in 1939 plus 2134 with modern coordinates, spinning at the astonishing rate of 641.93 times per second, giving it a period of just 1.558 milliseconds. This discovery revolutionized pulsar astronomy and opened new avenues for research. At such rapid rotation rates, the surface of a neutron star near its equator moves at approximately 25% of the speed of light. The centrifugal forces are enormous, nearly tearing the neutron star apart, balanced only by the intense gravity of its compressed matter. If the neutron star were even slightly less compact, rotational forces would overcome gravity and the star would disintegrate. The stability of millisecond pulsars thus provides constraints on the equation of state of ultradense matter in neutron star interiors. When astronomers first discovered millisecond pulsars, they noticed several peculiarities that distinguish them from normal pulsars. First, millisecond pulsars have much weaker magnetic fields, typically about 1,000 to 1,000,000 times weaker than those of young pulsars. Second, they slow down at extraordinarily small rates, with period derivatives often measured in units of billionths of a nanosecond per second. Third, many millisecond pulsars are found in binary systems with white dwarf companions, unlike most young pulsars, which are solitary. These clues pointed toward an evolutionary scenario quite different from the standard birth of a pulsar in supernova. The key to understanding millisecond pulsars lies in a process called recycling, where an old neutron star in a binary system is spun up through mass transfer from a companion star. This process begins billions of years after the neutron star's formation, when its original rapid rotation has slowed down considerably and it has ceased to be an active radio pulsar. If this old neutron star has a companion star that evolves to become a red giant, the giant star expands until its outer layers reach the point where the neutron star's gravity can capture them. Material from the companion star flows toward the neutron star, forming an accretion disk around it. As this matter spirals inward through the disk, it gradually transfers angular momentum to the neutron star, spinning it up to faster rotation rates. Over millions of years of accretion, the neutron star can be spun up from a rotation period of seconds or longer to millisecond periods. The accreted material also partially screens the neutron star's magnetic field, effectively burying the field lines and reducing the surface magnetic field strength. When accretion eventually ceases, either because the companion star has exhausted its envelope or because the system configuration changes, the neutron star is left spinning rapidly with a weak magnetic field. This recycled pulsar, now rotating hundreds of times per second, crosses back over the death line and becomes detectable again as a radio pulsar, but now as a millisecond pulsar. The weak magnetic field means the pulsar will slow down very gradually, remaining active for billions of years into the future. The companion star, having lost much of its mass to the neutron star, typically ends its life as a low-mass white dwarf in orbit around the millisecond pulsar. The discovery of millisecond pulsars in binary systems with white dwarf companions strongly supports this recycling scenario. In many cases, the orbital period, companion mass, and system characteristics match predictions from binary evolution models. Some systems show evidence of having gone through multiple episodes of mass transfer, creating complex evolutionary histories. Particularly interesting are systems called Black Widow pulsars and Redback pulsars, named after spiders. In these systems, the millisecond pulsar's intense radiation and particle wind bombard a low-mass companion star, gradually evaporating it. Black widow pulsars have very low mass companions, often just a few % of the sun's mass, which are being ablated by the pulsar. Redback pulsars have somewhat more massive companions. These systems represent ongoing stages of evolution that may eventually leave the millisecond pulsar alone, its companion completely evaporated. Some millisecond pulsars are found in globular clusters, ancient spherical collections of hundreds of thousands of stars packed into regions just tens of light years across. The high stellar densities in globular clusters increase the probability of interactions between stars, including the formation of binary systems containing neutron stars. Globular clusters are rich hunting grounds for millisecond pulsars, with some clusters containing dozens of known millisecond pulsars. The rotational stability of millisecond pulsars is truly extraordinary. The best millisecond pulsars show timing stabilities of about 1 part in 10 to the 15th power over timescales of years. This means that after tracking a millisecond pulsar's pulses for several years, astronomers can predict the arrival time of future pulses to within tens of nanoseconds. This stability rivals or exceeds that of the best atomic clocks on Earth. This remarkable stability has made millisecond pulsars invaluable as cosmic timepieces. Astronomers use arrays of millisecond pulsars, called pulsar timing arrays, to search for subtle effects that would be impossible to detect with single pulsars or even with atomic clocks on Earth. The most ambitious application is the search for gravitational waves, ripples in space-time predicted by Einstein's general relativity, using pulsar timing array methods. The physics of millisecond pulsars also provides insights into matter under extreme conditions. The rapid rotation and large mass of millisecond pulsars constrain the equation of state of neutron star matter. Observations of the most massive neutron stars, some of which are millisecond pulsars with masses around twice the sun's mass, rule out certain models of nuclear matter and provide crucial data for nuclear physics in regimes inaccessible to terrestrial laboratories. Some millisecond pulsars show remarkably complex orbital dynamics. A pulsar designated PSRJ0337 plus 1715 is in a hierarchical triple star system with 2 white dwarf companions. The inner white dwarf orbits the pulsar every 1.6 days, while both orbit a more distant white dwarf every 327 days. This system provides unique opportunities to test general relativity in strong gravitational fields with multiple bodies. The discovery and study of millisecond pulsars have revealed that neutron stars can have multiple lives. Born in violent supernovae and initially spinning rapidly, they gradually slow down over millions of years. Then, if circumstances are right, they can be reborn through mass transfer, emerging as millisecond pulsars with rotation rates and stabilities that make them nature's most precise clocks. These recycled pulsars will continue timing the cosmos for billions of years, long after their younger cousins have spun down and fallen silent. The extraordinary timing precision of pulsars, particularly millisecond pulsars, has made them invaluable tools for testing fundamental physics, especially Einstein's theory of general relativity. General relativity, published in 1915, describes gravity not as a force, but as the curvature of space-time caused by mass and energy. While the theory has been tested extensively in the weak gravitational fields of the solar system, pulsars provide opportunities to test it in much stronger fields and in situations involving rapidly moving massive objects. The first major test of general relativity using pulsars came from the binary pulsar PSR B1913 plus 16, discovered in 1974 by Russell Hulse and Joseph Taylor using the Arecibo radio telescope. This discovery would ultimately earn them the Nobel Prize in Physics in 1993, marking the first time pulsars were recognized by the Nobel Committee for their contributions to fundamental physics. PSRB 1913 plus 16 consists of two neutron stars orbiting each other every 7.75 hours, with one of them observable as a pulsar. The orbit is highly elliptical, with the two stars approaching as close as 740,000 miles at their nearest point, about 3 times the Earth-Moon distance. Despite this seemingly large separation, in astronomical terms, this is incredibly close for such massive objects, each containing about 1.4 times the Sun's mass. As Hulse and Taylor monitored this system over months and years, they observed several relativistic effects predicted by general relativity. First, they detected the advance of periastron, a shift in the orientation of the elliptical orbit similar to but much larger than the perihelion advance of Mercury's orbit observed in the Solar System. In PSR B 1913 plus 16, the orbit's orientation shifts by 4.2 degrees per year, more than 100 times larger than Mercury's advance and measured with exquisite precision. They also observed gravitational redshift and time dilation effects. As the pulsar moves through different parts of its orbit, its distance from the companion neutron star changes, varying the gravitational field it experiences. The changing gravitational potential causes time to run at different rates, making the pulsar appear to speed up and slow down in a precisely predictable way. Additionally, the pulsar's varying orbital velocity creates special relativistic time dilation effects. All these predictions matched general relativity's predictions to high precision. Most remarkably, Hulse and Taylor discovered that the orbital period was gradually decreasing, meaning the two neutron stars were spiraling closer together. According to general relativity, two massive objects in close orbit should emit gravitational waves, ripples in spacetime that carry away energy and angular momentum from the system. This energy loss should cause the orbit to decay, bringing the stars gradually closer together. The measured rate of orbital decay matched Einstein's predictions with extraordinary accuracy. After years of observations, the agreement between theory and observation reached better than 1%, providing compelling indirect evidence for the existence of gravitational waves decades before their direct detection. This was a triumph for general relativity and demonstrated the power of pulsar timing to test fundamental physics. The binary pulsar system will eventually merge, about 300 million years in the future, when the neutron stars spiral together and collide. Such mergers are thought to be sources of short gamma-ray bursts and are now known to produce gravitational waves directly detected by instruments like LIGO. They may also be the primary sites where many of the universe's heavy elements, including gold and platinum, are created through rapid neutron capture processes. Since the discovery of PSR B 1913 plus 16, astronomers have found other binary pulsar systems that provide even more stringent tests of general relativity. The double pulsar system PSR J0737-3039 discovered in 2003, contains two detectable pulsars orbiting each other every 2.4 hours. This unique system allows astronomers to study the system from multiple perspectives and has enabled tests of general relativity effects at even higher precision. In PSR J0737-3039 both neutron stars are observable as pulsars, though the second pulsar is detectable only intermittently. The presence of two pulsars allows measurements that are impossible in single pulsar binaries. For example, astronomers can measure the Shapiro delay, an effect where light takes longer to travel through curved spacetime near a massive object. As one pulsar's signal passes near the companion neutron star on its way to Earth, the travel time is delayed by an amount that depends on the companion's mass and the system geometry. The double pulsar system also shows extremely rapid orbital decay due to gravitational wave emission, with the orbital period decreasing by about 7 milliseconds per year. The system provides multiple independent tests of general relativity, including measurements of 5 post-Keplerian parameters, orbital effects that deviate from simple Newtonian physics. All measurements are consistent with general relativity to precisions better than 0.05%, representing some of the most stringent tests of Einstein's theory in strong gravitational fields. Pulsars have also enabled tests of gravitational wave propagation. According to general relativity, gravitational waves should travel at the speed of light. By observing both gravitational waves and electromagnetic waves from the same event, specifically the neutron-star merger GW170817 detected in 2017, astronomers confirmed that gravitational waves travel at the speed of light to within 1 part in a quadrillion. Millisecond pulsars provide unique tests of relativity in triple-star systems. PSR J0337 plus 1715, a millisecond pulsar orbiting 2 white dwarf stars in a hierarchical triple system, allows tests of the strong equivalence principle, which states that strongly self-gravitating bodies like neutron stars should fall in external gravitational fields the same way as less gravitationally bound objects. Measurements from this system have confirmed the strong equivalence principle to unprecedented precision. Pulsar timing also tests alternative theories of gravity. While general relativity has passed every test, physicists continue to explore alternative theories that might explain phenomena like dark energy or provide quantum corrections to Einstein's classical theory. Many alternative theories predict deviations from general relativity that would be observable in pulsar timing, particularly in strong field or high-velocity regimes. The agreement between pulsar observations and general relativity constrains these alternative theories. The use of pulsars to test fundamental physics extends beyond general relativity. Pulsar timing arrays search for ultra-low-frequency gravitational waves from supermassive black hole binaries in distant galaxies. These gravitational waves, with periods of years, would cause correlated changes in the arrival times of pulses from many pulsars across the sky. While not yet definitively detected, pulsar timing arrays have placed important limits on the gravitational wave background. Pulsars also provide tests of quantum gravity effects, though these remain speculative. Some theories suggest that space-time might have a discrete structure at extremely small scales, which could cause dispersion in the propagation of gravitational waves or electromagnetic radiation, similar to how light disperses in a prism. The sharp pulses from pulsars, traveling across thousands of light years, provide sensitive probes for such effects, and no evidence for quantum space-time structure has been found. The binary pulsar systems continue to provide new insights as timing baselines extend over decades. PSRB 1913 plus 16 has now been monitored for nearly 50 years, and the accumulated data provides ever more precise tests of general relativity. The orbital decay measurement now agrees with general relativity to better than 0.2%, an extraordinary confirmation of Einstein's century-old theory in one of the most extreme environments accessible to observation. As pulsar discoveries continue and timing precision improves, these cosmic lighthouses serve as laboratories for fundamental physics, testing our understanding of gravity, space-time, and the behavior of matter and energy under conditions impossible to replicate on Earth. Each pulse from a distant neutron star carries information about the fabric of space-time through which it has traveled, making pulsars indispensable tools for probing the fundamental nature of the universe. Beyond testing Einstein's theories, pulsars serve another crucial scientific purpose: mapping the structure of our Milky Way galaxy. As radio waves from pulsars travel through interstellar space on their way to Earth, they interact with the dilute gas and magnetic fields that fill the space between stars. By studying these interactions, astronomers can use pulsars as probes of galactic structure, measuring distances, mapping magnetic fields, and revealing the distribution of matter throughout our galaxy. One of the most important applications of pulsars in galactic cartography involves determining their distances from Earth. Unlike stars, whose distances can often be measured through parallax, pulsars are too far away for parallax measurements to be useful in most cases. Instead, astronomers use a property of radio wave propagation through plasma to estimate pulsar distances. This method relies on a phenomenon called dispersion. As radio waves travel through the ionized gas, or plasma, of the interstellar medium, they experience a delay that depends on their frequency. Lower frequency radio waves are slowed more than higher frequency waves, causing different frequencies to arrive at different times even though they were emitted simultaneously by the pulsar. By measuring the time delay between the arrival of high and low frequency components of a pulsar signal, astronomers can determine the dispersion measure, which quantifies the total amount of ionized gas along the line of sight to the pulsar. To convert a dispersion measure into a distance, astronomers need to know the average density of electrons in the interstellar medium. This has been estimated through observations of many pulsars with known distances, creating models of electron density distribution throughout the galaxy. These models, such as the NE 2001 and YMW16 models named for their developers, provide three-dimensional maps of electron density that allow distances to be estimated for newly discovered pulsars. The distribution of pulsars reveals important features of galactic structure. Most pulsars are concentrated near the galactic plane, the flattened disk where most of the galaxy's stars, gas, and dust reside. This makes sense because pulsars are born in supernova explosions of massive stars, and massive stars are found primarily in the galactic disk where star formation occurs. The scale height of the pulsar distribution, the distance above and below the galactic plane within which most pulsars are found, is about 600 light-years, somewhat larger than the distribution of their progenitor massive stars. Some pulsars have high velocities relative to the average motion of stars in the galaxy. These high-velocity pulsars are thought to have received kicks during their birth in asymmetric supernova explosions. The kicks can be substantial, with velocities of hundreds of miles per second, enough to carry pulsars far from the galactic plane over millions of years. By studying the distribution of pulsars at different distances from the galactic plane and combining this with their ages estimated from spin-down measurements, astronomers can study the velocity distribution of neutron stars and learn about supernova explosion mechanisms. Pulsars also serve as probes of the galactic magnetic field. The radio waves from pulsars are polarized, meaning the electromagnetic fields oscillate in preferred directions. As these polarized waves travel through magnetized plasma in the interstellar medium, the plane of polarization rotates, an effect called Faraday rotation. The amount of rotation depends on the strength of the magnetic field along the line of sight and the amount of ionized gas, as well as the frequency of the radio waves. By measuring the Faraday rotation toward many pulsars distributed across the sky, astronomers can map the structure and strength of the galactic magnetic field. These observations have revealed that the Milky Way has a large-scale magnetic field aligned roughly along the spiral arms, with additional random or turbulent components on smaller scales. The field strength in the interstellar medium is about a few microgauss, millions of times weaker than Earth's magnetic field, but extending over vast distances and containing enormous total energy. The distribution of pulsars in the galaxy also reveals something about star formation history. Young pulsars, identified by their rapid spin-down rates and associations with supernova remnants, trace recent supernova activity. Their concentration in spiral arms and star-forming regions reflects the current sites of massive star formation. Older pulsars have had time to drift away from their birth locations, creating a more dispersed distribution that reflects both their initial distribution and their subsequent motions through the galaxy. Some pulsars are found in globular clusters, ancient spherical collections of stars orbiting in the galactic halo. Globular clusters contain old stars, typically 10 billion years or more in age. Yet they harbor numerous millisecond pulsars. This apparent paradox is resolved by the recycling process. Old neutron stars and binary systems within the dense cluster environment are spun up through mass transfer, creating millisecond pulsars long after the original pulsar would have ceased radio emission. The study of pulsars and globular clusters provides insights into stellar dynamics in dense environments. The high stellar densities in cluster cores increase the probability of close encounters between stars, leading to binary formation and exchange interactions where stars swap partners. Some cluster pulsars show evidence of having acquired their companion stars through such exchange interactions rather than evolving from primordial binary systems. Pulsars discovered beyond the Milky Way in nearby galaxies like the Magellanic Clouds and the Andromeda Galaxy extend pulsar studies to different galactic environments. These extragalactic pulsars, though more difficult to detect due to their greater distances, provide information about star formation, supernova rates, and interstellar conditions in other galaxies. The similarities and differences between pulsar populations in different galaxies help astronomers understand how galactic environment affects stellar evolution and neutron star formation. The spatial distribution of pulsars, combined with their velocities and ages, allows reconstruction of the history of star formation and supernovae in the Milky Way. By tracing pulsars backward in time using their measured motions, astronomers can determine where they were born and identify regions of past supernova activity. This provides a fossil record of star formation extending back millions of years, complementing observations of current star-forming regions. Pulsar surveys continue to discover new pulsars, refining our understanding of the galactic pulsar population. Modern surveys using sensitive radio telescopes can detect pulsars throughout much of the galactic disk and even in the galactic halo. Each new discovery adds to the catalog of positions, distances, and properties that collectively paint a picture of the galaxy's structure and the distribution of matter and magnetic fields in interstellar space. Some surveys have discovered pulsars in unusual locations or with unexpected properties, revealing the diversity of the pulsar population and the complexity of neutron star evolution. Isolated millisecond pulsars, rotating rapidly but lacking binary companions, suggest evolution scenarios more complex than simple recycling. Pulsars with strange spin-down behavior or unusual pulse profiles challenge standard models of pulsar emission and magnetosphere physics. As pulsar surveys become more sensitive and cover larger areas of sky, the census of galactic pulsars grows. Estimates suggest that the Milky Way contains hundreds of thousands of active pulsars, though only a few thousand have been discovered so far. Most remain undetected either because their beams don't happen to sweep across Earth or because they're too faint for current telescopes to detect. Future surveys with next-generation telescopes will discover many more, further refining the galactic census. The use of pulsars as cosmic cartographers demonstrates how these rapidly spinning neutron stars serve science in multiple ways. Not only do they provide precision tests of fundamental physics and serve as stable timekeepers, but they also act as probes scattered throughout the galaxy, each one providing information about the matter, magnetic fields, and structure of the interstellar medium along its particular line of sight. Together, they create a comprehensive map of the Milky Way, revealing our galaxy's hidden architecture. One of the most unexpected discoveries in pulsar science came in 1992 when astronomers Alexander Woolsey and Dale Frail announced the detection of planets orbiting a pulsar. This finding was astonishing for several reasons. It marked the first definitive discovery of planets beyond our solar system, predating the first exoplanet found around a normal star by 3 years. Moreover, the existence of planets around a pulsar seemed paradoxical, given the violent supernova explosion that creates the neutron star should destroy any pre-existing planetary system. The discovery emerged from careful timing observations of pulsar PSR B1257 plus 12, a millisecond pulsar with a rotation period of 6.2 milliseconds located about 2,300 light-years from Earth. Woolson and Frail were monitoring this pulsar to study its timing properties when they noticed subtle periodic variations in the arrival times of pulses. These variations indicated that the pulsar was moving in space, wobbling back and forth in a complex pattern that could only be explained by the gravitational influence of orbiting planets. The timing data revealed 3 planets orbiting the pulsar. 2 of them, designated PSRB 1257 plus 12b and c, have masses several times that of Earth and orbit at distances of 0.36 and 0.46 astronomical units for the pulsar, roughly comparable to Mercury's distance from the Sun in our solar system. A third planet, designated PSRB 1257 plus 12a, is much smaller, with a mass similar to Earth's moon, and orbits closer to the pulsar. Later observations suggested evidence for a possible fourth planet even farther out, though its existence remains uncertain. The detection method relies on the extraordinary timing precision possible with millisecond pulsars. As the planets orbit the pulsar, their gravitational pull causes the pulsar itself to orbit the common center of mass of the system. This motion means the pulsar is sometimes slightly closer to Earth than average, and sometimes slightly farther away. Light travel time differences of just a few tens of microseconds, created by these small orbital motions, are detectable in high-precision timing data. By measuring the periods and amplitudes of these timing variations, astronomers can determine the orbital periods, semi-major axes, and minimum masses of the planets. For the PSRB 1257 plus 12 system, the orbital periods are 25.3 days, 66.5 days, and 98.2 days for planets A, B, and C respectively. The orbits appear to be nearly circular and lie approximately in the same plane, similar to the architecture of our own solar system. The discovery raised immediate questions about how planets could exist around a pulsar. The supernova that created the pulsar should have destroyed any pre-existing planetary system, either through the violence of the explosion itself or through mass loss that would unbind planetary orbits. Several formation scenarios have been proposed to explain pulsar planets, most involving formation after the supernova rather than survival through it. One possibility is that pulsar planets form from a debris disk created by material falling back onto the neutron star after the supernova explosion. The supernova would eject most of the star's outer layers into space, but some fraction of the ejected material, particularly from equatorial regions, might not achieve escape velocity. This material would fall back, forming a disk around the newborn neutron star from which planets could gradually coalesce, similar to planet formation around young stars, but in a much more exotic environment. Another scenario involves the disruption of a companion star. If the supernova progenitor was in a binary system, the explosion could partially disrupt the companion without completely destroying it. Material from the disrupted companion would form a disk around the neutron star, potentially allowing planet formation. This scenario is consistent with some millisecond pulsars, which were likely spun up through mass transfer from companions that may have been partially or completely destroyed in the process. A third possibility, specific to some systems, is the complete destruction and accretion of a companion star. In binary systems where a neutron star accretes material from a companion over long periods, the companion may eventually be completely consumed, leaving only a disk of material from which planets might form. This could explain planets around millisecond pulsars, which are known to be recycled through accretion processes. The environment around a pulsar is extraordinarily hostile to planets. The intense radiation from the pulsar, including X-rays and high-energy particles, would severely irradiate any planetary surfaces. The planets in the PSRB 1257 plus 12 system receive about as much energy from the pulsar's radiation as Earth received from the Sun, but in a much more dangerous form. Any atmospheres would likely be stripped away by the pulsar wind, and surfaces would be heavily processed by radiation. Despite these harsh conditions, the pulsar planets appear to be stable over long timescales. The orbits show no signs of decay or significant evolution, suggesting the system has reached a dynamically stable configuration. Gravitational interactions between the planets do occur, causing small variations in their orbital periods that have actually been detected in the timing data. These interactions provide independent confirmation of the planet's existence and allow astronomers to constrain their masses more precisely. Since the discovery of the PSRB 1257+12 system, a few other pulsar planet candidates have been reported, though none are as well established as the original three. Some binary millisecond pulsars show timing variations that might indicate the presence of planets, but confirming these detections requires long-term monitoring to distinguish genuine orbital variations from other effects like timing noise or magnetospheric changes. The discovery of pulsar planets predated and in some ways enabled the exoplanet revolution that began in earnest with the 1995 discovery of 51 Pegasi b, the first planet found orbiting a sun-like star. The pulsar planet discovery demonstrated that high-precision astronomical measurements could detect planets through their gravitational influence on their host stars, validating techniques that would soon be applied to search for planets around normal stars. Interestingly, while thousands of exoplanets have now been discovered around normal stars, pulsar planets remain rare. Only a handful of systems are known or suspected, making them unusual outcomes in stellar evolution. This rarity might reflect the difficulty of forming planets in post-supernova environments, or it might simply be that most pulsar planetary systems remain undetected because they require both suitable system configurations and very long-term, high-precision timing observations to reveal. The existence of planets around pulsars demonstrates the resilience and ubiquity of planet formation processes in the universe. Even in the aftermath of one of the most violent events in nature, and in the hostile environment around a neutron star, planets can form and persist. This suggests that planetary systems might be even more common and diverse than previously imagined, forming not only around sun-like stars, but also in exotic environments we are only beginning to explore. The study of pulsar planets continues to provide insights into planet formation, orbital dynamics, and the history of individual pulsar systems. Each new observation adds details to our understanding of these unusual worlds. While we will likely never directly image these planets or study their surfaces with spacecraft, they remain fascinating subjects that expand our conception of what constitutes a planetary system and where planets can exist in the cosmos. Among the thousands of known pulsars, a special subset stands out for pushing the limits of rotation: the fastest spinning pulsars, which rotate at rates approaching the theoretical maximum for neutron stars. These ultra-rapid rotators, spinning hundreds of times per second, test our understanding of neutron star structure and demonstrate the extreme physics possible in the universe. The fastest known pulsar rotates at an astounding 716 times per second, completing a full rotation in less than 1.5 milliseconds. This fastest known pulsar, designated PSR J 1748-2446 AD, was discovered in 2006 in the globular cluster Terzan 5, located about 18,000 light-years from Earth toward the constellation Sagittarius. The discovery was made using the Green Bank telescope in West Virginia during a survey of globular clusters searching for millisecond pulsars. The extraordinary rotation period of 1.396 milliseconds corresponds to an equatorial velocity at the neutron star surface of approximately 24% of the speed of light, assuming a typical neutron star radius of about 12 miles. At such extreme rotation rates, the neutron star is nearly at the breakup limit, the maximum rotation speed beyond which centrifugal forces would overcome gravity and tear the star apart. The breakup limit depends on the neutron star's mass distribution and the equation of state of ultradense matter, making observations of the fastest pulsars valuable constraints on nuclear physics. The fact that PSRJ 1748-2446 exists and is stable implies that neutron star matter must be sufficiently rigid to withstand these enormous stresses. The rotation rate of PSRJ 1748-2446 also approaches another theoretical limit related to gravitational wave emission. According to general relativity, a rapidly rotating neutron star with any asymmetry in its mass distribution will emit gravitational waves, losing rotational energy. If the asymmetry is large enough, gravitational wave emission could balance the spin-up torque from accretion, preventing the neutron star from spinning faster regardless of how much mass it accretes. The maximum observed rotation rates suggest that neutron stars are remarkably smooth, with any mountains or asymmetries limited to heights of less than a few millimeters. Most of the fastest spinning pulsars are found in globular clusters, dense collections of old stars where stellar interactions are common. The high stellar density increases the probability of neutron stars encountering and capturing companion stars from which they can accrete mass and angular momentum. This recycling process spins up the neutron stars to millisecond periods, creating the population of ultra-fast rotators observed in clusters. The distribution of pulsar spin periods shows an interesting pattern. Most millisecond pulsars have periods between 1.5 and 10 milliseconds, with relatively few spinning faster than about 1.5 milliseconds. This suggests that something limits how fast neutron stars can be spun up, either gravitational wave emission, the breakup limit, or perhaps changes in the accretion process at extreme rotation rates. Understanding this distribution helps astronomers learn about neutron star physics and binary evolution. Some of the fastest pulsars show complex rotational behavior. PSRB 1937+21, which held the record as the fastest known pulsar from its discovery in 1982 until 2006, shows timing noise and small irregularities in its rotation despite its millisecond period. These variations might arise from processes in the pulsar's interior, possibly involving the superfluid neutron matter that likely exists in the core. Studying these variations provides rare insights into the interior structure of neutron stars. The fastest pulsars are also among the most stable natural clocks. Despite rotating at rates that seem impossibly fast, they maintain their rotation with extraordinary regularity. Some millisecond pulsars show timing stabilities of better than 100 nanoseconds over years of observations, meaning we can predict the arrival time of a pulse years in advance to within a tenth of a microsecond. This stability reflects both the physical robustness of neutron stars and the minimal torques acting on isolated millisecond pulsars. Observations of the fastest pulsars contribute to fundamental physics in several ways. The maximum observed spin rate constrain the equation of state of nuclear matter at supernuclear densities, helping to distinguish between different theoretical models. The stability of these extreme rotators tests our understanding of neutron star structure and the forces that can affect rotation. The distribution of spin periods in the pulsar population informs models of binary evolution and mass transfer. The discovery of increasingly fast pulsars has been enabled by improvements in telescope sensitivity and signal processing capabilities. Detecting a pulsar spinning hundreds of times per second requires rapid sampling of the incoming radio signal and sophisticated algorithms to search through the data for periodic signals. As techniques improve, astronomers can detect fainter pulsars and search with finer period resolution, potentially revealing even faster rotators if they exist. Some theoretical models predict that the fastest pulsars might emit continuous gravitational waves if they have small asymmetries. These gravitational waves would be monochromatic, with frequencies twice the rotation frequency, and could potentially be detected by instruments like LIGO and Virgo after integrating signal over long observation periods. While no confirmed detection has been made, these searches continue and would provide unique information about neutron star structure if successful. The study of fast pulsars also illuminates the late stages of stellar evolution in dense stellar environments. The presence of many millisecond pulsars and globular clusters, some of them in exotic binary systems, reveals the complex interactions that occur in these ancient stellar populations. Some clusters contain dozens of millisecond pulsars, making them rich laboratories for studying pulsar populations and stellar dynamics. Occasionally, fast pulsars are found to have unusual properties that challenge theoretical understanding. Some show unexplained timing variations or mode changes where their emission properties suddenly shift. Others have magnetic fields stronger or weaker than expected for their spin periods. Each discovery adds nuance to our understanding and sometimes requires revision of theoretical models. The fastest spinning pulsars represent an extreme of stellar evolution, the end product of a complex sequence of events including star formation, stellar evolution, core collapse supernova, binary interaction, and mass transfer. That nature can create objects spinning nearly 1,000 times per second, yet maintaining such extraordinary rotational stability demonstrates the remarkable physics possible under extreme conditions. These cosmic speed records continue to inform and challenge our understanding of matter, gravity, and stellar evolution. As we conclude our journey through the story of pulsars, from their serendipitous discovery to their role as cosmic timekeepers and laboratories for fundamental physics, we reflect on how these extraordinary objects have transformed astronomy and our understanding of the universe. Pulsars represent one of those rare discoveries that opened entirely new avenues of research and continue to yield insights more than 50 years after Jocelyn Bell Burnell first noticed that unusual signal in her chart recordings. The discovery of pulsars revealed that the universe contains objects of almost unimaginable properties. Stellar remnants no larger than cities, yet containing more mass than the Sun, spinning at rates of hundreds of revolutions per second, possessing magnetic fields trillions of times stronger than Earth's, and emitting beams of radiation that sweep through space with the regularity of the finest clocks. The very existence of such objects challenges our everyday intuitions and expands our conception of what is physically possible. From an astronomical perspective, pulsars have proved invaluable as tools for studying the universe. They serve as cosmic laboratories where we can observe matter under conditions of extreme density, temperature, and magnetic field strength that can never be replicated on Earth. They provide tests of general relativity in strong gravitational fields, confirming Einstein's century-old theory with ever-increasing precision. They map the structure of our galaxy, revealing the distribution of matter and magnetic fields in interstellar space through the ways their signals interact with the material between the stars and Earth. The extraordinary timing stability of millisecond pulsars has enabled their use in pulsar timing arrays, networks of pulsars monitored regularly to search for ultra-low frequency gravitational waves from supermassive black hole binaries in distant galaxies. While these gravitational waves have not yet been definitively detected, recent observations suggest we may be on the verge of detection, which would open another window on the universe and reveal processes involving the most massive objects in the cosmos. Pulsars have also provided unexpected discoveries, like the first confirmed detection of planets beyond our solar system, demonstrating that planets can form even in the hostile aftermath of stellar explosions. This expanded our understanding of where planets can exist and showed that planetary systems are diverse and resilient, forming in environments we had not imagined. The study of pulsars has driven technological advancement in radio astronomy. The need to detect and time faint, rapid pulses has led to developments in telescope sensitivity, signal processing algorithms, and timekeeping methods. These advances benefit many areas of astronomy and technology beyond pulsar studies, demonstrating how fundamental research drives innovation. Educational impacts of pulsar discoveries have been substantial. The story of pulsars captures imagination and communicates several important lessons about science. The value of careful observation and attention to unexpected signals, as demonstrated by Bell Burnell's discovery. The power of theoretical prediction and understanding, as physicists had predicted neutron stars decades before their observational discovery. And the iterative nature of scientific understanding, as each new observation refines and sometimes challenges our theories. Looking to the future, pulsar astronomy continues to evolve. Next-generation radio telescopes like the Square Kilometre Array, currently under construction in South Africa and Australia, will detect pulsars throughout the Milky Way and even in nearby galaxies, vastly increasing the known population. These new discoveries will refine our understanding of pulsar populations, stellar evolution, and galactic structure. Improved timing capabilities will enable even more stringent tests of fundamental physics. Networks of millisecond pulsars timed to nanosecond precision over decades will potentially detect gravitational waves from the early universe or from cosmic strings, hypothetical one-dimensional defects in space-time. They will test alternative theories of gravity and search for evidence of physics beyond the standard model. Space-based X-ray observatories continue to study X-ray pulsars, revealing the high-energy emission from these objects and providing information about conditions near the neutron star surface. Some of the most interesting pulsars emit more energy in X-rays than radio waves, and understanding the full electromagnetic spectrum of pulsar emission remains an active area of research. Theoretical work continues to refine our understanding of pulsar emission mechanisms, interior structure, and evolution. Despite decades of study, fundamental questions remain about how pulsars generate their coherent radio emission, what the precise structure of neutron star interiors is, and what determines the diversity of pulsar properties. Each new observation provides data to constrain theories, gradually converging on comprehensive models. The long-term monitoring programs that track pulsars over years and decades are building invaluable datasets. These extended baselines reveal subtle effects and allow detection of phenomena that only become apparent over long timescales. Some pulsars have been monitored continuously since their discovery in the 1960s and 1970s, providing 40 or 50 years of data that document their long-term evolution and stability. In a broader sense, pulsars remind us of the universe's grandeur and the power of scientific inquiry. These objects, formed in violent stellar deaths and spinning in the darkness of space, send their signals across hundreds or thousands of light years, preserving timing information with exquisite precision. That we can detect these signals, interpret them, and use them to probe the fundamental nature of space, time, matter, and gravity demonstrates the remarkable capability of human curiosity and ingenuity. As you drift towards sleep, imagine the thousands of pulsars scattered throughout our galaxy, each one a rapidly spinning neutron star, each one sending its lighthouse beam sweeping through space. Some of those beams happen to cross Earth, allowing us to detect them and decode their messages. Each pulse represents one rotation of a city-sized stellar remnant. Each precise timing measurement contributes to our understanding of the cosmos, and each discovery reveals new facets of the universe's beautiful complexity. The story of pulsars is ultimately a story about discovery, persistence, and the deep human drive to understand the universe we inhabit. From the careful observations of a graduate student noticing an unusual signal, through decades of theoretical development and technological advancement, to the current era where pulsars serve as precision tools for fundamental physics. This story demonstrates science at its best: curious, rigorous, creative, and endlessly revealing. The pulsars continue their ancient dance, spinning in the darkness, beaming their signals into the cosmos, keeping time with a precision that spans the galaxy. They are nature's most accurate clocks, monuments to the extreme physics possible in our universe, and testament to our ability to observe, understand, and learn from even the most distant and exotic phenomena. As the universe expands and evolves, these cosmic timekeepers continue their steady rhythm, measuring the passage of time in one of the most precise ways nature has devised, and inviting us to continue our exploration of the cosmos. They help us understand. And so our journey through the story of pulsars concludes, though the pulsars themselves continue, spinning, pulsing, illuminating the nature of space and time for as long as we care to listen to their precisely timed messages from the depths of space.